Hey everyone, welcome to this explainer. I am absolutely thrilled you're here. Today, we're jumping right into this interactive study guide to demystify, well, honestly, one of the most miraculous materials on Earth, the semiconductor. We're going to take a journey together from the totally invisible realm of subatomic energy bands all the way up to the practical circuitry that's literally powering the device you're using right this second. We're going to figure out exactly how a seemingly inert chunk of silicone gets manipulated to connect our entire world. Let's get into it.
So here's our roadmap for today. We'll start with the solid-state revolution, move right into the conductivity cliff, and then explore doping as an energy shortcut. After that, we'll bring it all together with the PN junction, the one-way valve, and finally see how we go straight from atoms to usable power.
All right, Section 1, the solid-state revolution.
Just think about the sheer contrast here. On one side, we've got the legacy vacuum tube. Now, these things literally had to boil off electrons and needed a physical vacuum space just to work. They were super bulky, ran extremely hot, and required a massive amount of voltage. But then look at the other side. That's the solid-state paradigm shift, an integrated circuit stamped onto a microscopic silicon wafer. No vacuum, no crazy heat. The electrons flow entirely within this solid crystal lattice structure. It's incredibly low power, low voltage, and just ridiculously reliable. I mean, this single shift right here, it is the absolute foundation of our modern portable world.
Moving right along to Section 2, the conductivity cliff. Before we can actually build a chip, we really need to establish the basic rules of electricity, right? So to understand electronics, we first have to look at how different materials handle electrical flow. On one end, we have metals, like copper. Electricity flows through them completely effortlessly. Over on the other end are insulators, things like glass or diamond, which just completely block that flow. But sitting right there in the middle, that's where the magic happens, semiconductors. They have this intermediate resistivity, which basically means we can actually control and tune their conductivity artificially. It's a total game changer. Now, the whole key to this control comes down to something called the energy gap. You can kind of think of this as a microscopic conductivity cliff. It's literally a gap that electrons have to leap across before they can actually do any useful work for us. To put that into perspective, let's look at how this works. In metals, the band where electrons are normally trapped actually overlaps with the conduction band, so electrons just flow freely, almost like water moving across a totally flat surface. Super easy. In insulators, though, that energy gap cliff is massive. We're talking greater than 3 electron volts. There is no way they're jumping that. But in semiconductors, the gap is just small enough to be jumpable. In silicon, for example, it's a tiny 1.1 electron volts. With just a little bit of thermal energy, electrons can hop right over this tiny cliff, leaving behind a really fascinating phenomenon down in the valence band. Which brings us to Section 3, doping, the energy shortcut. This is where the story really gets good, how we manipulate these pure crystals to make them incredibly useful. But before we actually dope the crystal, we need to wrap our heads around a simple analogy for a pretty complex quantum behavior. We call it the hole. When an electron jumps that energy cliff we just talked about, it leaves behind an empty space in the atomic lattice. Think of it like a completely sold-out movie theater, right? If someone in the front row gets up and leaves, there's suddenly an empty seat. If the person behind them moves forward into that seat, well, the empty seat appears to move backwards. So, watching this play out, when a bound electron moves left to fill a vacancy, that vacancy, the hole, actually appears to move to the right. Now, the hole isn't a physical particle, it's just an empty space, but it effectively acts exactly like a positive charge. And here's the crazy part. Inside our semiconductor, the total electrical current is actually the sum of these independent electrons flowing one way and those apparent holes flowing the exact opposite way. Now, pure silicon on its own just doesn't have nearly enough of these free electrons and holes to be practically useful for us at room temperature. It really needs some help. Enter doping. This is the totally ingenious process of deliberately injecting specific atomic impurities right into the silicon lattice. And we're talking tiny amounts here. Doing this at just a few parts per million radically increases the conductivity, and it does it without destroying the underlying crystal structure. There are basically 2 totally different ways to dope our silicon. First is N-type, or negative doping. This is where we inject an element like phosphorus, which happens to have 5 outer electrons. Silicon only needs 4 to bond, so that 5th electron basically becomes a free agent, totally free to move around. Then on the flip side, we have P-type, or positive doping. Here, we inject an element like boron that only has 3 outer electrons. this instantly creates a missing bond, an acceptor hole. So just like that, we've created two radically different materials. So, you might be wondering, why go through all this trouble? Well, because doping creates an energy shortcut. Remember that 1.1 electron volt conductivity cliff from earlier? By adding these impurities, we essentially build a stepping stone right inside that gap. Instead of making the electrons do a massive, difficult leap, it now takes a negligible 0.05 electron volts of thermal energy to get things moving. We've literally turned a giant, impassable wall into a tiny, effortless step.
All right, let's move into Section 4, the p-n junction.
We now have N-type materials absolutely packed with free electrons, and P-type materials packed with free holes. So what happens when these two distinct worlds finally collide? Well, it happens in three distinct steps. First, initial contact is made. Second, a massive diffusion process begins. And third, a stable depletion region forms. Let's look at exactly what that actually looks like.
Okay, first up we have our initial contact. The p-type is full of holes and the n-type is full of electrons. Now, because of this massive concentration gradient, the electrons naturally just rush right over the border to fill those holes. This is that diffusion process we just mentioned. But as they cross the border and cancel each other out, they leave behind these immobile charged ions. This creates a physical barrier that we call the depletion region. It establishes this built-in electric field that actually stops any further flow. Basically, we've just built an atomic wall.
So here we are. We have a stationary piece of silicon with a microscopic atomic barrier right in the middle. I mean, it's fascinating for sure, but as it sits there, it doesn't really do much. So the million-dollar question is, how on earth do we manipulate this stationary wall to actively control electricity? That brings us to Section 5, the one-way valve. The answer lies in realizing that this p-n junction isn't just a static wall. When we hook it up to an external power source, it suddenly becomes a dynamic one-way door for electricity. We call this a diode. By applying a voltage, a process known as biasing, we can actually manipulate that depletion region. In forward bias, we apply positive voltage to the P side and negative to the N side. This shrinks the depletion region, drops that barrier, and allows massive amounts of current to flow. But watch what happens in reverse bias. If we flip the battery around, we pull the carriers away from the junction. The barrier grows wider, and the flow of electricity is completely choked off. This single curve right here really tells the whole story of the diode. Look at the reverse bias side. The current stays flat at almost zero. It's acting like a perfect wall. But over in forward bias, once we exceed that tiny 0.7 volt atomic barrier, the curve just shoots straight up. The diode suddenly acts like a totally frictionless valve, letting current flow super easily. It is literally a one-way street for electricity.
And finally, Section 6, from atoms to usable power.
Now that we have our one-way valve, we are ready to zoom all the way out to the macro level to see how this actually powers your world. The electricity coming from the wall outlet into your house is alternating current, or AC. It constantly reverses direction, acting completely wild and wavy. But your laptop, your phone, they absolutely need steady, single-direction, direct current. So how do we fix this? Well, we do it by cleverly arranging our p-n junction diodes. In a full-wave rectifier circuit, the diodes act kind of like tiny traffic cops. They chop up and redirect the negative cycles, literally forcing all the current to flow in a single direction to create a pulsating DC output. Looking at the big picture here, this perfectly synthesizes everything we've learned today. Right down at the atomic scale, we use chemical doping to manipulate quantum behaviors and jump that energy gap. That creates the p-n junction at the component scale, or dynamic one-way valve. Then we arrange those valves into a rectifier at the circuit scale, add a capacitor to smooth it all out, and boom. At the macroscopic output, you get the pure, steady DC power that's required by pretty much all modern electronics. It is a totally seamless journey from a tiny atomic anomaly to a massive technological triumph.
It really makes you look at your computer a little differently now, doesn't it? Just knowing that right now, right beneath the glass and metal of the screen you're looking at, billions of these invisible atomic barriers are seamlessly shrinking and widening. They're controlling DC electricity to power the logic gates that literally compute our world and deliver this very explainer to you. Absolutely wild. Thank you so much for learning with me today. Keep asking questions, keep studying, and I will catch you in the next explainer.